A colligative property is just a property of a solution. It's a property that affects the solvent, but not the solute, all right? And the first one we're going to look at is what happens when a solute is placed in a solvent and it lowers the vapor pressure of the solvent. Now, volatile means that you have a liquid with an appreciable vapor pressure over it. And most of the time, the solvents are volatile. They'll have a vapor pressure over it. Once in a while, if you have a really heavy molar mass substance, you won't, but most of the time you do, okay? So I'm going to show you a video here in a second with two little Erlenmeyer flasks. They're both capped, but the left-hand side has only purple solvent molecules. And you can see that there are purple solvent molecules in the liquid, and there's also purple solvent molecules above the liquid. So the ones above the liquid would be the vapor pressure, and the ones dissolved in the liquid there, those would be the solvent molecules. Then we're going to look at the same set of conditions on the right-hand side, but those red molecules are solute particles. We're going to assume that the solute is non-volatile. It doesn't have a gas pressure of itself, but it will affect the gas pressure of the solvent over the solution while we're set. Now, we're also going to see how this is affected once the liquid vapor equilibrium hits. That just means that you've given them enough time for the vapor pressure to establish it. Pretty cool. So let's see how this is going to work with our examples here.
The vapor pressure of a liquid depends on the ability of the liquid's molecules to break intermolecular forces and escape into the vapor phase. A molecule can escape only when it has enough energy and is at the surface of the liquid. When a non-volatile solute is added to a liquid, some of its molecules occupy surface sites in the liquid, displacing volatile solvent molecules. Because fewer solvent molecules get to the surface, fewer can escape, and the vapor pressure of the solution decreases.
So again, on the left-hand side, you're seeing a normal solvent, and most solvents are volatile, which means they have a vapor pressure over them. And so if you have a closed system, then eventually this equilibrium happens between the liquid and the gas phase. You're going to have some vapor pressure over the solvent, no problem. That's how most solvents are. On the right-hand side, though, we're adding a non-volatile solute. So non-volatile means that the solute doesn't have a very big vapor pressure, so it doesn't have red molecules floating above the solution, basically, which is the case with a lot of solutes. But anyway, the red solute molecules block the liquid solvent molecules from going into the gas phase. The solute red molecules, they don't care if the purple molecules in the gas phase go to the liquid phase. That's not a problem. But they do prevent the liquid molecules from going into the gas phase. So what happens, solutes tend to block the solvent going from liquid to the gas phase. So you end up with less liquid molecules in the gas phase over the solution, and what that means is your vapor pressure is lowered. So if you were to measure the pressure on the left-hand side Erlenmeyer there without the solute, it would be a higher number than the vapor pressure of the solvent on the right-hand side where you have a solution. So in a solution, the vapor pressure of the solvent is lower than it is if you have the vapor pressure of a pure solvent. I like to think about the solutes as being like blockers at a nightclub, or bouncers, all right? Like they're like, they look at people and they say, oh no, the club is full, you can't come in. But once in a while, they'll let people in. They're popular, which I never understand because I'm not popular. But anyway, that's a personal problem. Anyway, the blockers, the bouncers, prevent a lot of people from going into the club. Now, people can go out of the club anytime they want. That would be like gas going to liquid. But they don't let a lot of people go into the club unless you're special. All right. That's a really dumb analogy, but it does kind of reflect here how the solvent molecules have a problem going from liquid to gas when the solute's present. They are literally bouncing them back into the solvent, and it takes extra energy to let the liquid molecules, the solvent liquid molecules, get into the gas phase. So at the end of the day, the vapor pressure of the solvent is lower in a solution than it is in a pure solvent. This leads to this expression right here, which is a little weird, but we're going to go through it. And what it says is you have a P0 on the right. P0, the zero symbol usually means pure in science. So that's saying that the vapor pressure of the pure solvent, that's what the little zero means right there. And if you take the vapor pressure of the pure solvent at that temperature and multiply it by the mole fraction, there's our chi we talked about earlier, the mole fraction of the solvent, that will give you the vapor pressure of the solvent in the solution, which is what we see on the left-hand side. So remember that mole fraction is a fraction. It can go as low as 0, it can go as high as 1, but it will never be more than 1. So what that says is whatever your vapor pressure of the pure solvent is, that's always going to be probably a bigger number, or at least the vapor pressure of the solution will be no bigger than it. So that means it's been lowered, all right? So they call this vapor pressure lowering, all right? The vapor pressure of the solvent in the solution will be less than the vapor pressure of the pure solvent. Those bouncer, those blocker solute molecules are preventing the liquid from going into the gas phase. So you have less gas over the liquid. That's where the vapor pressure lowering comes from. On the right-hand side in that picture right there, the big blue molecules, those are the solutes, the bouncers, the blockers, whatever. And they're blocking the water molecules from getting from the liquid to the gas phase. So on the left side, where there's no solute, lots of water molecules in the gas phase. But on the right side, when the solute's present, not as many liquid molecules in that gas phase. That means you're going to have a lower vapor pressure when the solution is present relative to the vapor pressure. The vapor pressure of the solvent over the solution is P solvent, the part on the left. And that equals the mole fraction of the solvent, not the mole fraction of the solute, mind you, but the mole fraction of the solvent, times the vapor pressure of the pure solvent. That P0 means pure vapor pressure. And in a nutshell, what that means, solution vapor pressure will be less than pure solvent vapor pressure. Raoult was the scientist that first figured this out. The vapor pressure is lower in the solution than it is in the pure solvent. And at first you might think, oh yeah, whatever. But actually there's some pretty cool kind of consequences from Raoult's law we'll talk about. And sometimes when people want species to evaporate, they will use Raoult's law to figure out the new value of how much vapor pressure is over the solution to make them evaporate easier. So there's a lot of uses for Raoult's law, as it turns out. So here's an example using Raoult's law. Let's use the same material from before. We had ethylene glycol, 62.1 grams. We placed it in 250 grams of water. We calculated that the mole fraction of the ethylene glycol was 0.0672. Anyway, let's figure out what the vapor pressure of water will be in the ethylene glycol solution at 30 degrees Celsius. All right. Now, why the 30 degrees Celsius value is important is you can look up the vapor pressure of water at almost any temperature. And at 30 degrees Celsius, if you look it up, the vapor pressure of pure water, 31.8 millimeters of mercury. So to figure this out, we need to figure out P solvent. That's going to be the vapor pressure of water in the solution. And that's going to equal mole fraction of solvent times vapor pressure of pure solvent. And 31.8 is P0 solvent. All right, that's the vapor pressure of the pure solvent. The answer we're going to calculate will probably be a number less than 31.8. So that's another kind of cool thing to keep in mind. Earlier, we calculated the mole fraction of the ethylene glycol, 0.0672, and we want the mole fraction of the water. Now, you could take moles of water and divide it by moles of ethylene glycol plus moles of water. However, if there's only two components, then mole fraction of ethylene glycol plus mole fraction of water will equal 1. So if you go 1 minus the mole fraction of the ethylene glycol, that gives you the mole fraction of the water, 1 minus 0.0672, mole fraction of water, 0.9328. So that's the chi solvent value that we need. And I want to point out once again, this is mole fraction of solvent, not mole fraction of solute. A lot of times when we deal with concentrations, we're more interested in solute, but in this case, focus on the solvent. 0.9328 mole fraction of solvent times the vapor pressure of the pure solvent, 31.8, that comes out to be 29.7 millimeters of mercury. So let's think about what these numbers mean for just a second. In pure water at this temperature, vapor pressure 31.8 millimeters of mercury. But in this solution here with ethylene glycol, where we have the bouncers, the blockers, the ethylene glycols, they're preventing some of the water in the liquid phase from getting to the gas phase. So the vapor pressure is lower. It's 29.7 when it was 31.8. This is the vapor pressure lowering phenomena. The vapor pressure of the solvent is lower in the solution than it is in the pure solvent. Okay, so here's a question. This has iodine, I2, in carbon tetrachloride, CCl4. And it says the vapor pressure of the pure carbon tetrachloride, 504 millimeters of mercury. What's the vapor pressure of the CCl4 over the solution? All right, so before we start this problem, let's just identify what's going on here. Carbon tetrachloride is the solvent. It has a vapor pressure, 504 millimeters of mercury at 65 degrees Celsius. And what we're doing here is we're putting a solute, iodine, in the carbon tetrachloride. So iodine is the solute, carbon tetrachloride is the solvent, and we have here an iodine in carbon tetrachloride solution. All right, so what we're looking here for the vapor pressure of the solvent, carbon tetrachloride, over the solution. So we'll use the vapor pressure in the solution equals the pure vapor pressure, which is this number right here, 504 millimeters of mercury, times the mole fraction of the solvent. So we have here 1.96 moles of carbon tetrachloride, and we have 0.0400 moles of iodine. So we're going to calculate mole fraction first. That'll be 1.96 moles of solvent divided by total moles, which is 1.96 plus 0.04, which happens to be 2. So it's like 1.96 divided by 2. That's going to be the mole fraction of the solvent. We'll then multiply that by the 504 millimeters of mercury value to give one of the answers listed down there. Now, before we start, though, the final vapor pressure of the solvent in the solution will be a number less than 504. So right away, you don't have to worry about A or B. A would be the vapor pressure of the pure solvent, but we have a solution. It's going to be lower. And 514 is a greater number than 504, and that doesn't happen by anything known to chemists. It's always going to be a value less than. Now, 10.1 and 1.96 seem pretty small to me, so my money here would be on 494 millimeters of mercury. Do the math to make sure. But if you do that, lo and behold, of course I knew what the answer was. I'm the instructor. But anyway, the answer, sure enough, C, 494 millimeters of mercury. So what I did here, this part right here, that's the mole fraction of the solvent. It's moles of solvent divided by total moles, moles of solvent plus moles of solute, and that comes out to be 0.980. And you multiply that by the vapor pressure of the pure solvent, 504. Sure enough, 494 millimeters of mercury. Good to go. Once in a while, you can have a volatile solute or volatile solutes. And if you have to figure out then what the total vapor pressure is, you can absolutely do it. It's just a little extension. So in Raoult's law, if you have not only a solute, but a solvent, which is volatile, and remember, volatile just means you have a vapor pressure over the solution. Then you just do mole fraction of the first one times the vapor pressure, pure vapor pressure of the first component, and you add it to the mole fraction of the second one times the vapor pressure, pure vapor pressure of the second one. And if you have a third one, you can do C, et cetera, et cetera, et cetera. So let's figure out here how this all works. In this problem, we have both heptane and octane, and both of these have a torr value. So those are vapor pressures. A torr and a millimeter of mercury are the same. So if they have a vapor pressure listed, that means that they're volatile. They're going to have a little bit of vapor pressure. And we want to do this so that we want to calculate the total vapor pressure of the system, but it also says that the mole fraction of the heptane is 0.15. So as we talked about earlier, with two component systems, mole fraction of the first plus mole fraction of the second equals 1. So we're going to first calculate then the mole fraction of the other component, which is the octane. So in this problem, if the heptane mole fraction is 0.15, the octane will be 1 minus that, or 0.85. And then what you want to do is just multiply the respective vapor pressures by their mole fractions. So if 31 torr is the heptane, we'll multiply that by 0.15, the mole fraction of the heptane. And then to that, we'll add the mole fraction of the octane times its vapor pressure, which is 11 torr in this problem. Multiply them together, add them up. 14.1 torr is the total vapor pressure in the mixture. So if you do have a volatile solute or something like that, you can absolutely calculate it. It's not too crazy. A little tedious perhaps, yes, but nothing you can't handle, and keep that in the back of your mind. The first of the cligative properties was vapor pressure lowering, which is Raoult's law. But now what we're going to do is talk about what's much more helpful to chemists most of the time, honestly, which is changes to the boiling and freezing points of different solutions. And we're going to again focus on the solvent in these, but it's an amazing kind of process, and it is related to the vapor pressure. First, just some definitions. Boiling is where the solvent begins to go from the liquid to the gas phase. And condensing or freezing is where the solvent, which is a liquid, will start to go into the solid phase. So boiling and freezing. As you put solute in a solvent to make a solution, we're going to see that the boiling and freezing points will change. And they're changing by an amount, delta T. And delta is the difference between the boiling point of the solution and the boiling point of the pure solvent. Or if it was for freezing, it would be the difference between the freezing boiling point of the solution versus freezing point of the solvent. Here's one thing that's going to be really important. Your delta T should always be positive, all right? Don't use negative delta T's. It just gets too confusing. In some books, there's a constant K that's given, and if the K values are negative, then that's where the delta T's are negative. But it just makes your life so much easier if you always remember to have a delta T, which is positive, all right? So in the case of boiling, then, to get a positive, boiling points we're going to see are higher. It would be the solution minus the pure solvent. But for freezing points, it's usually better to do the solvent minus the solution. We'll talk about that here in a little bit.
At 30 degrees Celsius, pure water and a solution of ethylene glycol have nearly the same vapor pressure. As temperature increases, so do both vapor pressures. But when the vapor pressure of water reaches 1 atmosphere, ethylene glycol is at almost half that. Pure water boils at a significantly lower temperature than does the ethylene glycol solution.
This video shows the effect of having an ethylene glycol solution versus pure water. And we're looking here at the normal boiling points. Now, water has a normal boiling point, which is where the vapor pressure equals 1 atmosphere of pressure. It has a normal boiling point of 100 degrees Celsius. All right, no problem. However, if you have a car radiator, it's easy to get to a temperature that's more than 100 degrees Celsius, and you may not want your water to start boiling. So what people will do is they'll put some kind of antifreeze in it. Ethylene glycol is one possible antifreeze. There are a couple different ones that go in there. But anyway, the red curve then is for a solution. And solute molecules, which in this case ethylene glycol, are blocking the solvent water molecules from going to the liquid to the gas phase. So what that means is your vapor pressure, the y-axis, is lower. All right. So at the same point there, you can see that the solution, roughly that point right there, that solution has a much lower vapor pressure than you would have at pure water. So if you keep going on the red line over to that point, you can see that the solution then has a boiling point, which is more like 115 degrees. So what this means, your boiling point of the liquid, the solvent, will be higher in the solution than it was was with the pure solvents. So we'll talk here in a little bit about how boiling points are elevated. Boiling points will be higher in a solution than they will be if you had pure solvent. So water boils at 100 degrees Celsius. Ethylene glycol plus water will boil at 115 or so. Now, for boiling point elevation, to figure it out, delta T, which is the boiling point difference between the solution and the solvent, delta T equals K times M. And K is just a constant. You never have to worry about it. There's a value for water over here we'll talk about in a second. I will give you those K values, or you can look them up and stuff, no problem. But little m there is molality. So molality, moles of solute over kilograms of solvent. And from this point, you can figure out how much higher your boiling points will be, stuff like that. So in this example, let's use that ethylene glycol and water example again. 62.1 grams, which was 1 mole, in 250 grams or 0.250 kilograms of water. And the question is, what's the boiling point of the solution? Now, you do have to look up a K value. K values are based on the solvent. So this is water, no problem. The value is 0.512. The units are weird. Don't worry about that. Molality will be moles of solute over kilograms of solvent. So that's 1 mole of ethylene glycol divided by 0.250 kilograms, 4.00 molal. We calculated this earlier, no big deal, but just a good refresher. And we need this value because delta T, the change in the boiling point temperatures, equals that weird K constant times the M. So when you calculate it then, 0.512 times 4.00, delta T 2.05 degrees Celsius. And what this tells you then, water normally boils at 100 degrees Celsius exactly, and you add that delta T to it, your solution will boil at 102.05 degrees Celsius. So again, higher than the boiling point of the pure solvent will be. So delta T equals K times M. You have to calculate M to find delta T. K values you can look up, or I'll give them to you, no big deal. Freezing points have a very similar looking expression, but freezing points, of course, are lowering instead of raising. And what's happening in freezing points is those crazy solutes are blocking the solvents from going from the liquid to the solid phase. But the equation looks really similar. So delta T equals K times M for freezing point lowering, just like delta T was K times M for boiling. But remember, at freezing point, the solution will be lower, while a boiling point will be higher in the solution. So delta T, which sometimes gets a little symbol F instead of B for freezing versus boiling, it's the difference between the freezing point. K is just a constant. It's a different constant than you have for the boiling point. So you have to look up a different thing, but again, you don't need to worry about that. And little m is molality. So I want to show some videos here on the right that shows what's happening in freezing with a pure solvent versus a solution. And in this video, they use pure water on the left and a ethylene glycol water solution on the right. But one problem with this video is that it shows the ice as being more dense than the liquid water, i.e. your ice cubes sink to the bottom. And as you know, by putting an ice cube in water, the ice will float on the water. It's less dense. Hydrogen bonds, we talked about it, et cetera, et cetera. So the videos aren't perfect, but the idea is really valid. Most compounds, the solid phase is more dense than the liquid phase, so this would be legit, but it's not legit with water, alas. But anyway, let's see how this works here, and I'll talk about it.
When water freezes, its molecules leave the liquid phase and attach to other molecules in the solid phase. At the freezing point, an equal number of molecules move into and out of the solid phase. A solution of ethylene glycol, automobile antifreeze, has a freezing point lower than that of pure water. Molecules of the solute block the interface between the solid and liquid phases, thus decreasing the rate at which molecules leave the liquid phase and attach to the solid.
So on the left-hand side again, except for the bad thing about ice sinking in water instead of floating, but same idea if it would float, by the way. But anyway, you have a constant equilibrium between liquid molecules going to the solid phase and solid phase molecules breaking off and going to the liquid phase. And that's what freezing is all about. However, when you have a solute, the ethylene glycol, those little yellow atoms on the right, they once again are acting as bouncers or blockers, and they're preventing the liquid from going to the solid phase. They don't care about the solid going to liquid phase. That's not a problem, but the liquid going to solid phase is definitely important. So if they're blocking it, you have to lower the temperature quite a bit to make the liquid molecules continue to bond with the solid. So the punchline here is that a solution will have a lower freezing point than that of the pure solvent. So if water normally freezes at 0 Celsius, the solutions might have a freezing point of, say, -5 degrees Celsius, something lower than that. So it's pretty cool. So a solution will have a higher boiling point than a normal solvent. It'll have a lower freezing point than a normal solvent, and it will have a lower vapor pressure than the regular solvent. Here's an example of a freezing point question, and again, it's very similar to the boiling point. It's going to be another delta T equals K times M. We will use a different K value. Freezing point constants are different than boiling point, so this would be something you'd look up. I highly recommend that you let your delta T be a positive number all the time. So let's figure out the freezing point of our 4.00 molal ethylene glycol water solution we've been using so far. No problem. Delta T equals K times M. It's that weird freezing point constant times 4.00 molal. The delta T, 7.44 degrees Celsius. Now you have to remember that water, which we'll use a lot, 0 Celsius. And this shows how much lower the freezing point will be relative to the pure solvent. So what that means here is that the freezing point of the solution, 7.44 degrees less than 0, minus 7.44 degrees Celsius. Now again, a lot of times books will use negative KF values because they think you should calculate a negative delta T, etc., etc. I wouldn't do that. I would just make your delta T positive all the time. If you get a negative number, just absolute value it. And absolute value your K value if you happen to run into a negative K value. Molality is based on mass, grams, moles, that kind of stuff. And in chemistry, mass can never be negative, all right? So molality must be a positive number. So if you really want to do delta T is negative and K is negative, that's fine. Just make sure that your molality is a positive number. It can't be. But again, what I would do, delta T, just make it a positive number. You have to realize it's going to be lower than whatever the freezing point is. Not too bad. So in this question, we have the following aqueous solutions, and you want to know which one's going to have the highest freezing point. And pure water, sodium chloride, sugar, sulfuric acid, blah, blah, blah. And delta T equals K times M. K is based on the solvent. They're all supposedly water. M is the molality. So in one way, it might be tempting to say answer D because that's the highest molality. But remember, freezing points are lowered in solutions relative to the solvents. So the higher molality would have a lower freezing point. Boiling freezing points are being lowered. So when you think about this long enough, this is a trick question. The pure water will have a higher freezing point than all of the other ones, all right? Because the water, the pure solvent, always has higher freezing points than the solutions that are made from it. So in this one, water will have a higher freezing point than all of the solutions and stuff that are there. Freezing points are lowered in solutions relative to the pure solvent. Keep that in the back of your mind. At this time, it's worthwhile to remember that ionic compounds will dissociate. They don't just dissolve, they dissociate into their ions. And because these colligative properties depend on the number of particles, this becomes important. So sometimes you see an extension to all the laws we've seen so far where they have what's called the Van Hoft factor, and it gets the symbol I. So as an example for the freezing point we just did, delta T equals K times M times I, where I is the Van Hoft factor. Now, so far in all the examples we've done, all of our compounds have been covalent. And covalent compounds, nonmetals and nonmetals, you don't have positives and negatives derivatives pointing it out, and that's why I've used them intentionally. However, you can absolutely use ionic compounds as well, as long as you consider the Van Hoff factors. So if you have a covalent molecule, I is 1 all the time. So ethanol and acetone and DNA and caffeine and all these things that, sugar for that matter, all the things that dissolve in water that have nonmetals and nonmetals, covalent bondings, they all have just 1. However, sodium chloride breaks up into Na plus and Cl minus. 2 particles, 2 ions per NaCl. So the Van Hoff factor would be 2 because you have 2 pieces for every NaCl that breaks up. That's why your I factor is different. Now for magnesium chloride, you'd have a magnesium 2 plus and 2 chlorides in solution. So 1 magnesium and 2 chlorides, 3 pieces total. I factor is 3. So notice that you're adding up the number of ions to find the I factor. Aluminum chloride would be 4 because you'd have aluminum and 3 chlorides for 4 particles total, and it does affect freezing points, boiling points, stuff like that. Here's a question you might see. It says, how much sodium chloride have to dissolve to have in 4 kilograms of water to lower the freezing point to minus 10 degrees Celsius? And there's the Kf value again for it. So delta T equals K times M times I. Now, delta T is going to be the difference between pure solvent and the solution. I'm going to absolute value it. So 10 degrees lower would be a 10 degrees delta T positive. And so in this case then, delta T would just be 10. NaCl breaks up into Na plus and Cl minus, 2 ions per NaCl, so I is going to be 2. And we have the K value there, so let's use all this information to calculate the molality, which is this number right here, 2.68817. That's the moles of sodium chloride per kilogram of solvent. It's the molality that we solve for there. And if you multiply moles over kilograms by the kilograms of solvent, 4.00 kilograms, then that gives you the moles of the NaCl, which is this number. Multiply that by the molar mass of NaCl. It's going to take 628 grams of NaCl in 4.00 kilograms of water to lower the freezing point by 10 degrees. So this is just another twist of things. Now, we won't do tons of things with ionic compounds in water for colligative properties, but you might see one. So if you see one, just remember that I factor can be pretty important, and it's easy to figure out. You just literally count up the number of ions, that equals the I factor, no problem. I should note that we are only going to use what's called a theoretical I factor in Chemistry 222 and Chem 223. Sometimes there are actual I factors that are thrown around. If you see one, then definitely use it. But for us right now, we're going to use what's called theoretical, and that's where the number of ions literally equals the I factor. So in this question, it says which one will have the higher boiling point? And there's pure water, there's the sugar, and there's the NaCl. All right. Well, delta T, which is the change to the boiling point, equals K times M times I. Remember that. Pure water should have the lowest of the boiling points. All right, boiling points will get higher in solutions, not lower. So answer C is out. And then if you look at those two molality values, well, 0.15 molal for sugar is higher than 0.10 for sodium chloride, and it might be tempting to say the sugar is higher. Higher M should give you higher delta T, which is bigger boiling points. However, sugar is a covalent molecule. All carbons, hydrogens, and oxygens, I factor of 1. But sodium chloride is ionic, and in water it's going to break up into Na plus and Cl minus, an I factor of 2. So the I factor times the molality is what we should consider here to have the higher boiling point. So for sugar, that would be 0.15 times 1, which is just 0.15, and that's high, but it's not as high as 0.10 times 2, the I factor for NaCl, for sodium chloride. So in reality, answer A, the 0.1 molar NaCl should have a higher boiling point because of the I factor. So this is why those sodium chloride I factors can be pretty important. Just consider them in the back of your mind as you go through these problems. The best use of colligative properties, and honestly why we're talking about it more in this section than anything else, I guess, is because colligative properties can be used as a way to find the molar mass of the solute. And this is huge in chemistry. So finding the molar mass is really important. Allows you to go grams per moles. You can do limiting reactants, etc., percent yields, all that kind of jazz. So finding the molar mass is big. And there's a lot of instrumentation that does it, but it's also nice to have a chemical method to do it. So let's do an example here of how you can find the molar mass for a boiling point solution problem. So in this problem, all right, we've got this compound called azolene, and azolene is being dissolved in benzene. And by the way, these are both organic compounds, covalently bonded, so we don't have to worry about any of the I factors. But anyway, we're putting this azolene, 0.640 grams, in 99.0 grams of benzene, and the boiling point of benzene, which was 80.100 degrees Celsius, goes up to 80.230 degrees Celsius. Not a big amount, but it is enough to allow us to find the molar mass of azolene. So let's figure out how this works. So delta T equals K times M times I is the big expression. Well, delta T is the difference between the boiling points. And when you do that for benzene here, it comes out to be 0.130 degrees Celsius. Now, I is just 1 because these things are all covalent. We don't have to worry about that. And also, we have the K value there. It's a KB value. Oops, that says KM. That's a typo. Sorry about that. It's a K value. That's the important part. You don't need to worry about B's and F's like I do, obviously, as your instructor. Prophet back on. Anyway, we can solve for M. That's the idea. M is the molality. It's delta T over K times I technically, but I is just 1, so who cares? When you figure this molality out, 5.14 times 10 to the minus 2 moles over kilograms. Now, moles is going to be moles of solute, moles of azolene, and kilograms is going to be kilograms of solvent, kilograms of benzene. So if you take the molality and you multiply by the kilograms of benzene, 99 grams divided by 1,000 is 0.0990 kilograms. Kilograms times moles over kilograms gives you 5.05 times 10 to the minus 3 moles of solute. And that's moles of azolene. Well, we had 0.640 grams of azolene in this problem. So that grams divided by the moles we just calculated, 127 grams per mole is the molar mass of azolene. And this is a real cool way to kind of verify that the compound's molar mass that is using is the same as you think it is. Sometimes it's nice to have a physical method to balance the electronic methods that are used so often as well. We're going to use this expression quite often, and so a quick and dirty calculation, a way to find the molar mass for a problem like this, which by the way can be used in both boiling points and freezing points, is molar mass equals grams of solute times the K factor, whatever it is, divided by the delta T and the kilograms of solvent. So see if you can use this to get the 127 grams per mole number out. It certainly is a lot less work. It's one-stop shopping instead of doing it piecemeal, which is what we did right here. This also assumes, of course, that your I factor is 1. If you didn't have an I factor of 1, you could multiply the K by I to figure that out. But anyway, it's a nice kind of way to do it, and it might help on our lab coming up. The fourth of our colligative properties is called osmosis. And if you hear about osmotic pressure, it's the same thing. Osmotic pressure, osmosis, same thing. It's a colligative property. It's a property that affects the solvent. The solutes will act as blocker molecules, essentially, to make some weird things happen to the solvent, which is really crazy. Osmosis and osmotic pressure is super helpful to biochemists, and it is useful in chemistry in general, but biochemists, as we'll see, can really make some serious advantage of osmosis. In addition, osmosis is really helpful when it comes to finding potable water, like water that you can drink. You can actually take seawater and apply osmosis principles to it to get regular drinking water out. We'll talk about that a little bit. Osmosis is quite different in what it does relative to the other ones. But in osmosis, you generally have a solution on one side and a solvent, pure solvent, on the other. And in between them, you have a semi-permeable membrane. And the membrane allows solvent molecules to travel back and forth, but the solute molecules cannot go through the membrane. All right? So on the solution side, you have solute and solvent, and those solute molecules can't go to the solvent side, but the solvent molecules on the solution side can go to the solvent, and the solvent molecules on the solvent side can go to the solution. And what tends to happen is that solvent molecules rush into the solution side. So if you started with, say, 1 molar sodium chloride, you might end up with 0.5 molar sodium chloride, because the solvent is rushing to the solute side and it dilutes your solution. And it's just a wild phenomena, but this is something that scientists actually see. So those solvent molecules are moving from the solvent to the solution. It tries to make them both the same solution concentration, but it doesn't do that, because on solvent you'd have no solute, and the solute can't get through to that side. But at least tries to dilute the solution so it becomes more like water. It's a really wild phenomena, and we'll talk more about why this happens in a future lecture, but it is something that's observed by scientists, and it's amazing.
When a solution of higher concentration and a solution of lower concentration are separated by a semi-permeable membrane, one through which solvent molecules can pass but through which solute particles cannot, solvent molecules will pass through the membrane from the side containing the more dilute solution to the side containing the more concentrated solution. This process is called osmosis. Solvent molecules actually move through the membrane in both directions, but because the concentration of the solvent is higher on the right, solvent molecules on the right collide with the membrane more frequently than on the left, resulting in a net flow of solvent from right to left.
So in that video, it's like a YouTube, and not the fun YouTube where you can watch cat videos and stuff like that, but a true U-tube. It's a glass tube with that semi-permeable membrane in the bottom. And again, what happens is the solvent goes from either the side of pure solvent or the side that's less concentrated to the side where you have the solute, where it's more concentrated. So you end up seeing then like a higher pressure on the left side than you do the right in this example. And if you can measure that difference between the pure solvent and the solution, that's a millimeters of mercury, which is a pressure. So osmotic pressure is the pressure of the solvent on the solution, which is just totally crazy still when I think about it. On the left-hand side, this little picture, we've got a little sugar solution in that bag, and it allows, again, the water on the outside to move into the sugar solution, and the water on the sugar solution can go through the bag to the other side. But what you see is a net rushing of solvent molecules to the inside of the bag. So you end up measuring then this height right here, and it's the height relative to the baseline of the solvent. But anyway, it's a measurable pressure. It's a millimeters of mercury, all right? And this is what happens when you have osmosis. So it's a pressure. It's a pressure of the solvent, though. It's not a pressure of the gas like we did back in the gas laws, but it's just an amazing phenomena. It's something that can be observed over and over again. It's very cool. Osmotic pressure gets the symbol of Greek pi. Now, pi is confused sometimes with the 3.1416 number that's used in math, and this is a different use of pi. All right, it's not that pi. This is a pressure. So like pressure in the gas laws was given a capital P, osmotic pressure, the pressure of the solvent, gets this pi value here to represent it. It's a similar kind of idea, if you will. But anyway, pi, the osmotic pressure, is a pressure in atmospheres, and it's equal to ICRT, where I is the Van Hoff factor, which again is only applicable if you have an ionic compound. C is the concentration in moles per liter. We're back to molarity again, the good old king of the concentration units. R is the gas R, 0.082057, which is liters atmospheres per mole Kelvin, and temperature is the Kelvin temperature. And from all this, you can calculate then what the osmotic pressure will be. So on the right-hand side there, you can see in the solution, you have a measurable distance between the pure solvent and the solution. You can turn that millimeters millimeters of mercury into atmospheres using 760 millimeters of mercury, stuff like that. Totally amazing.
When a solution and a pure solvent are separated by a semi-permeable membrane, solvent can flow in both directions, but the solute cannot. Here, pure water moves into the solution, working to bring both the solution and pure water to the same concentration. This process, osmosis, continues until the flow of water across the membrane is balanced by the pressure exerted by the water column. A semi-permeable membrane blocks solute molecules, but allows solvent molecules to pass in both directions. The number of solvent molecules moving from the solution side to the pure solvent side is less than the number moving into the solution side, resulting in a net flow into the solution.
The solute molecules don't go through the membrane because they're either hydrated, like the waters go around, which makes them a lot bigger, or sometimes the molecules themselves are just bigger molecules, more atoms, all right? But for all those reasons, that's why they feel that they don't go through the semi-permeable membrane. But at the end of the day, like I showed on the left-hand video, you do have a pretty measurable distance between the solvent and where the solution stops, and it's usually a height. It's measured in millimeters of mercury. Yes, you could use inches, but don't use that in my class. But anyway, millimeters of mercury can be converted into atmospheres, and that's the pi of the osmotic pressure equation. So pi equals ICRT. Pi is the atmospheres, which comes from the measured distance that the solvent actually pushes it up. It's just fantastic to think about. This is an example of how you can use osmosis. It's a molar mass problem. And again, chemists just love finding the molar mass to make sure that their values are good. And earlier I said how the molar mass... And earlier I said how biochemists can use osmosis a lot, and this is how they use it. Small changes to osmotic pressure will create measurable molar mass calculations, and this is how this works out, so let's check it out. But anyway, in this problem we have 35 grams of hemoglobin, which is some big biomolecule, and you're placing it in water. You make a liter of solution, and after it settles, you found that the osmotic pressure pi is measured to be 10 millimeters of mercury at 25 Celsius. You can use this information to calculate the molar mass of the hemoglobin. So again, 10.0 millimeters isn't a huge amount, but it is something that's measurable, and we're going to use that to find the molar mass. So in this kind of a problem, what you have to do, because you're using the R, the gas constant R, you need to have the pressure in atmospheres. So 10 millimeters of mercury divided by 760 gives you 0.0132 atmospheres. That's the osmotic pressure of the solution. From that point, pi equals ICRT. Now I'm ignoring I here because hemoglobin is basically a big organic covalent molecule. Don't need to worry about it. And most of the time that's the case. So if you solve here for the concentration, which is moles per liter, concentration will be pi over RT. So there's R, 0.082057. Want to make sure you use Kelvin temperatures, so 298 Kelvin. And there's our pressure in atmospheres on top. And this comes out to be 5.40 times 10 to the minus 4 molar, which is moles per liter. Well, we have a liter of solution, so that means we have 5.40 times 10 to the minus 4 moles of solute. And 35 grams, the grams of solute, divided by the moles of solute we just calculated, comes up with the amazingly huge 64,800 grams per mole. And these biomolecules a lot of times have molar masses that are just incredibly large, like this one. Very normal for this type of field. In my field, molar masses usually go up to about 400 grams per mole, but in biochemistry, these numbers are very common. So just anyway, osmosis and osmotic pressure is a great way to figure out the molar masses of values of like this, which is pretty cool. Osmosis is really important, and I want to talk about some of the uses here real fast. And one of the important parts is in medicine. If you've ever had an operation, they hook you up to an IV right away, and the IV is not just pure water, which is actually good, as will turn out, because blood cells are like solutions. All right, they have different pieces inside the blood cell, and you want to have just the right amount of osmotic pressure, both outside the blood cell and inside inside the blood cell so you don't have the solvent molecules rushing around. So isotonic means that the concentration of the solute and solvent outside the cell are the same as inside the cell. And if you have that, you can see in that first picture right there, then you have just as many solvent molecules, probably water, going out as you have in, and that's good. Your cells are healthy, all is well and stuff, and you're good to go. However, you can have hypertonic, which is the second column, and you can have hypotonic, which is the third column. Now in hypertonic, all right, you have more solvent molecules going from the cell to the outside. So in those cases, you'd have a high concentration outside. The water molecules inside the cell are trying to equilibrate, so they rush out. So your cells shrink, and that's not good. That'll end up in cell problems. Also, you can have those hypotonics. That's if you had pure water that you were putting in instead of some kind of appropriate IV injection. And pure water then will rush inside your cells, make them bigger and bigger and bigger, and finally it's like a balloon, it'll burst and stuff like that, and that's bad news too. So medicine people, they have to make sure that all the solutions are isotonic, so it's good for you, and that's important. So yeah, so osmotic pressure is very important to living systems like you and me. Very cool. Water desalination is becoming a really important tool when you live in a city where there's not a lot of fresh water. And at first, this was mostly used in the Middle East, where it's very hot in desert-like conditions, and there wasn't a lot of water. They would take the seawater, and they would essentially pressurize it. And if you pressurize the seawater hard enough, then it forces what normally happens, which is water molecules going from pure solvent to the solution. If you pressurize it, and you can see it's greater than 30 atmospheres often, you can actually force the solvent molecules through the membrane, so you end up with pure water on the other side. So it's a way to desalinate the seawater, and you end up with drinking water. As water becomes more scarce, this is being used more and more. So Los Angeles has a quite active set of water desalination plants as well. And in the picture down there, you can see they got these big long tanks. They pressurize the seawater. Normal drinking water comes out one side, which is great, and then people can use it, et cetera, et cetera. It's not an easy process to set up, and of course it can be expensive. This is called reverse osmosis because you're not allowing what normally happens, which would be the pure water rushing to the solution, i.e. the seawater side. You're reversing the process, and it is not easy to do. You need really high pressures, but of course you need drinking water. Boy, no question about that. So this is something that's become more useful as society advances. Now, real fast, we're going to talk about colloids and suspensions. And normally, what chemists, at least in my world, usually use is we use just a solution. And solutions are the common kinds of traditional chemistry. Now, technically, a solution is when the solute particles are very small, 0.2 to 2 nanometers in diameter. And most salt water and salt solutions, acids, bases, stuff like that, those are normally what you have with solutions. However, there are also colloids. And colloids are also solutions. You have a solute and a solvent, but the particles are much bigger. So you can see in the middle picture there on the right-hand side, milk is actually a colloid, all right? It's a liquid, but you can't see through it because the pieces in the milk are bigger. They're usually roughly 2 to 1,000 or so nanometers, so much bigger than a traditional solution. So milk and fog is actually a colloid, lots of examples, but they are homogeneous. They're one phase, which is pretty crazy. A suspension has even bigger particles than that, and blood technically is a suspension, all right? It's not really just a colloid or anything like that. Paint, aerosol sprays, these are usually heterogeneous. You can usually see different kinds of particles inside them. So in the picture on the right there is mud. That's a good example of that. The mud particles can settle down. So solutions, colloids, and suspensions are all kind of in the same family. They have a type of solute and a type of solvent, but the properties are certainly different. And let's talk about the differences here as we go through this section. You can tell if you have a colloid versus a regular solution by what's called the Tyndall effect. And if you aim a type of a laser through a colloid, like that silver colloid suspension right there, you can actually see the light. In the pictures down there, it shows the laser going through first pure tap water, and there's no laser. You can't see the laser, it just goes through. However, if you have the colloidal silver, which is a colloid, then you can actually see the light go through. And the bigger particles are what allow the lasers to be determined, stuff like that. And there's a lot of examples of this around there. So for example, if you've ever been outside and you've seen what's called a Jacob's ladder, which is like the light streaming down from the sun, it's usually because the light is going through a type of fog or something and you can see it. And a lot of times the lights you see at night are all due to this kind of stuff, which is pretty cool. If you ever study colloids, they talk about solute and solvent a little bit different. They call their solutes a dispersed phase, and the solvents are called a dispersing medium, but it's the same idea. You have some kind of substance in a bigger substance. The dispersed phase is in the dispersing medium, similar to what a solute and a solvent is. And in this example right here, I'm showing lots of different kinds of examples of colloids, and these are things that are around us all the time. So like fog and smoke, milk, I talked about earlier, ink, foam rubber, jelly, cheese. All right, bronze, there's lots of different ones and stuff that are possible. And they have different types of names. So like aerosol, gel, foam, these are all types of colloids. And we're not going to spend a lot of times on colloids, but if you hear about any of these and you're curious, I totally encourage you to check them out and get more information.
In untreated cotton, surface hydroxyl groups attract each other and make for a rough surface. Fabric softener molecules are surfactants. Their polar heads are attracted to the hydroxyl atoms, leaving their nonpolar hydrocarbon tails out. The tails, because they display weak intermolecular force, can slide past each other, thereby imparting a soft texture to the cotton. In untreated cotton, surface hydroxyl groups attract water molecules, so cotton absorbs moisture. In cotton treated with softeners, however, some hydroxyl sites are occupied, making the fabric less attractive to water and therefore less absorbent.
There's quite elaborate chemistry on what's called a surfactant. All right, and a surfactant is basically a type of substance that promotes the formation of colloids, and it's pretty neat kind of stuff. A surfactant that's used for cleaning is called a detergent, and this is what we use to clean our clothes. And once when we talk about making clothes softer, clothes, which is most of the time cotton, is basically a series of hydroxyls, OHs. And like we've seen, OHs like to make hydrogen bonds. Hydrogen bonds on clothes with water tends to make also bonds, and that tends to make the clothes a little rougher. However, if you use these surfactants, they have basically a positive side that's ionic, or sometimes negative, but usually positive, I think. And then they have a long non-polar side, which is basically induced dipole. And if they can connect to the cotton, then you end up with the non-polar side sticking out. And the water molecules, which are very, very polar hydrogen bonded, don't like the non-polar part, so you don't have as many water molecules and everything is softer. This is a really cool field, and I'm not doing it justice to it in this particular part, but you can hopefully get a sense for how this stuff works out.
A soap micelle consists of a group of surfactant molecules with hydrophobic tails pointing inward and hydrophilic polar heads pointing outward. The micelle absorbs nonpolar oily liquids and carries them away as an oil in water colloidal dispersion.
Soaps and detergents are basically surfactants that have both a polar and a non-polar part to them, and it's really amazing. So let's say that you get a stain on your shirt. Well, if your stain happened to come from something ionic, then water should be able to wash it out, no problem. However, if you get a stain on your shirt and it's from an oil, like from a pizza, which I happen to love, but anyway, don't need to worry about that. Anyway, if you get something oily on your shirt, water won't do much with the oil because they have different intermolecular forces. So if you put this surfactant in, it usually will have a polar part and a non-polar part. So the polar parts are around the water and the non-polar parts kind of stick together in the middle. And what happens if you get to a stain on your shirt, then the non-polar parts will surround the stain and they'll essentially extract it then from the cotton shirt or whatever you happen to be wearing. And so what happens is these micelles form form. And the micelles have a polar part on the outside, which gets along well with water, so you can wash it away. On the other hand, on the inside, you've got non-polar parts, which can definitely extract the oils and stuff like that from your dirty clothes and wash them through. So it's a really cool kind of concept. But this is how stains are removed from clothes, which is fantastic. And scientists spend a lot of time trying to figure this out. That's an example of a surfactant up there. The structure, and you can see on the far right, is a sodium ion connected to an oxygen in a sulfate group. That's the ionic part. Like the oxygen with a negative there, that would be the negative part in the little micelle drawing. And then the rest of it is just a bunch of carbon-hydrogen bonds kind of going on for a long time. That would be the more non-polar part. Those would be the parts that would surround the oily stains and extract them from your clothes. Good to go. Okay, so that's it for Chapter 11. I really appreciate you spending your time with me, and I hope this has been a useful use of your time. There are certainly more materials for you to study this material. I highly recommend you check out the Solution Calculations handout so you get experience going from molality to weight percent and then eventually to molarity and all that kind of jazz, and that will certainly help you. Okay, if you do need assistance, feel free to reach out to me or the Learning Success/Avid Center located above the library on the Mount Hood Community College campus. We are all here to help you out big time. Thank you for spending your time with me. I really do appreciate it. Have a wonderful day.